next up for our topic of discussion about polynomials is division of polynomials and how to do that. So I'm going to assume that you guys are already familiar with how to take a polynomial, how to add them together, combine like terms. So subtracting, combine like terms in the same way, just make sure you're subtracting and applying the distributive property. And multiplying, you always have to FOIL as you're multiplying polynomials together. Division, however, is something that's not often taught very well or learned, and it's actually going to be really important as we progress further into our polynomials. So, in my experience, this is actually something I never learned how to do ever in high school. Somehow, I don't know if I just missed it or if my teachers never taught it, but it's a pretty important skill, and I think a lot of you I'm sure a lot of you know how to do it already, but it can be pretty challenging, and so I wanted to kind of give you my 10 cents, my 2 cents, whatever, on how to divide polynomials and how do we go about doing that. And it's super relevant as we move into the next couple sections when we talk about zeros, because we use division quite a bit. And there's also a shortcut synthetic division, which I want to cover very shortly too, which works sometimes it doesn't. I wanted to get into that. But basically, I wanted to review division of polynomials and focus on that for the next couple videos. And the first thing I like to start off with is if you know how to divide numbers, dividing polynomials is not so different. There are a few things to do, but I like to start really basic, because for me, if I'm ever forgetting the concept of how to divide, it's really no different than dividing normal numbers. So let's say I was just doing a random long division problem just for the sake of reviewing how to do division. And again, I'm assuming you guys know how to divide, but really I want to focus on terminology and implications, because all of the terminology is the same when we're dividing polynomials as it is for not for just dividing numbers. But basically the goal, right, is to figure out how many times this one goes into this one. And I don't know if you've ever thought about division. Technically, when you're doing division, you're not actually like computing division. Well, you are, but you're really figuring out how to multiply two numbers together to get the other number. So it's sort of a clever backhanded way of saying, well, how do I actually do division? We're really just doing a bunch of multiplying and subtracting. But anyways, I first take this number and I see how many times it goes into this. And right, the number of digits I use depends on the size of this number and the scale, right? So 13, you look for, I would need 2 digits. 13 goes into 54, and I can figure out, well, is that 3 or 4 times? I think it's going to be 4 times, right? Because 4 times 13, and obviously you could do this with a calculator, but that's defeating the purpose, because calculators cannot divide polynomials. Well, that's not true. Some more advanced calculators can actually do algebra. But yeah, 13 goes into 54 4 whole times with some remainder. But anyways, we figure out how many whole times it goes into it. We multiply through, which would be 52. And then we subtract to figure out what the remainder would be. So 54 minus 2 would be 2. And then we kind of rinse and repeat, keep going. Drop down the next number because I want to know, well, then how many times does 13 go into 22? Once, which would be 13. Subtract to get 9. Drop down the next number, 99. 13 goes into 99. I think 8 times. Again, you could, if you're not great with your times tables, I mean, who really knows how to multiply 13 really that well? Well, I was off. So 13 goes into 99 7 times fully. And 7 times 13 is 91. Actually, I do know that one. So I probably should have just thought about it more before guessing. But at the end of the day, you can use your calculator to help you if you really need to. Which would leave us with a remainder of 8. And then if I drop the 7 down, 13 will go into 87 6 times. Because it went into 7 times 13 was 91, so it's not enough to be 7. And 6 times 13 would be 78. Let's just go ahead and make sure so I don't mess anything up. 78. And I'm running out of space here, but minus 78 would give us 9. And then from there, technically, if we're using decimals, we could keep going, right? Because if I wanted to know what it would be, or if you just type it in your calculator, a lot of times it might give you a decimal answer, where technically you never have to stop division, because when you're dividing by prime numbers like 13, it actually creates a repeating decimal that never ends. So one of the issues with the decimal system of numbers is division can be kind of wonky, and sometimes numbers never go into each other in a pretty way. But in the case of polynomials, we often refer to what we have as the remainder, which is kind of like, back in grade school when you're learning about it, you say like R9, which is not really a very proper way of describing the answer to a division problem, but it's how we do it with polynomials because we don't have decimals. There's no such thing as like x.34, right? It doesn't make sense to use decimals within a polynomial. But the remainder is a lot more sensible. Anyways, let's go back and divide polynomials and talk about how this connects back to the start. And one other term is the remainder is what's left over at the end. And so a lot of times I might just put R as a shorthand for remainder, including with polynomials. Somehow I changed my pen there. 9 is the remainder. And often we call the result the quotient. That's the term for the result of the division problem. Same with polynomials, we call it's kind of like the answer. The remainder is part of the answer also, because what our conclusion here is that if we have a remainder, those two numbers were not divisible. They're only divisible if you get a whole answer. If it's not whole, it's not divisible. Just because it's not divisible doesn't mean we can't do it. It just means it doesn't really go into it perfectly as well. And the same thing is with polynomials. If we were to come up with a zero remainder, the difference there is we would say it is divisible and those two numbers go into each other. And the same thing is going to be the case with polynomials. If we get a zero remainder, that means divisibility, and there's a way that we can use that, which I'm going to talk more about. When we use division to help us factor polynomials shortly. But what was my point? Also, we often refer to the number out front as, well, either the denominator or the divisor, and the number on the inside as the dividend, what's being divided up upon. Again, those terms are not particularly important, but the thing that comes back together is that if you multiply the divisor together with the quotient, so there's a little formula I'm going to write that d times q plus r, what will happen is all those will add back together to get the original number. Because the goal of division, right, is to figure out how many times does this go into this. If I multiply these two back together, the idea is that those together will multiply to make this. Or if I were to take this divided by this, leaves me with this, right? It's the same thing, because if this divided by this is this times this should be equal to this by a basic equation. So when I have a remainder, that means that it doesn't quite go back together, and what I'm left with is something left over. And I just wanted to show you that this does work. If I take 13 times, and I think a lot of people do division without really thinking about the meaning of it. Notice what I get is, well, 13 times 4,176 is 54,288. And so what I can tell is, okay, that's not exactly my original dividend, but it's almost there. And if I were to add 9 to it, that's kind of like the missing piece that would reproduce that number. And so I know, well, there's 4,176 groups of 13 within this number, but there's 9 left over that didn't quite fit the bill. But basically, this is a formula that sometimes the homework will ask you to input your answer in this form. That's the reason I bring this back up. But you can always rewrite the original number by multiplying the two things back together, and if there is a remainder, adding that to the end. So with polynomials, that's the whole point of all this. But getting into division on a more detailed level than we normally would want to do. And yes, division is tedious. So I apologize that, in your homework, you're going to have to be doing a bunch of division. I'm not trying to bore you to death, but it is a necessary skill to work with polynomials. But with polynomials, basically, my point is we do very much the same thing. We start with the first number, or in this case, the first polynomial, and the goal is to then divide by the next thing, in this case, x minus 4. And a question is, well, are these divisible? What's the remainder? What's the quotient, etc.? Kind of the goals, things you could be asked to solve for. But in this case, it's slightly different, where what I did to begin with, right, is I wanted to see, well, how many times does this go into this? But notice I didn't take the whole thing, so you don't have to match this up with the whole polynomial, but what you can do is focus on specifically the leading term of each one. And what you want to do is figure out how many times does the leading term of the divisor go into the dividend, or the original polynomial and what I'm dividing by. And basically, we're going to, I like to say it as match, multiply, subtract. And that's kind of what I'm doing, right? I'm going to match them. I'm going to multiply them through after I match them. And then I'm going to subtract it down. Then I drop the thing and repeat. And so I'm just going to say this as MMS. That's probably not the right slogan, a good slogan. But basically, match, multiply, subtract, rinse, and repeat until I finish. And you'll see why we don't have to worry about the -4, because that's sort of like with the 13. 13 didn't perfectly go into 54, and when we subtract, we're going to take care of the rest later. Same thing with the -4. -4 might not go into 26, and we'll kind of take care of that later in the next step as we progress through the division problem. Anyways, if you're not good at saying, well, how many times does x go into 6x squared? Really, it's a pattern of matching both the coefficient and the x term. Instead of just matching numbers, well, what's nice about the coefficient of x minus 4 is it's just 1. So the way to match 1 and 6 is just, well, 1 times 6 would make 6. And matching x's is usually easy too. It's always just the difference in the degree. Because if I want to know, well, x times x is x squared. So if I took x times 6x, that would be 6x squared. And cool, that's step 1, match. Then, like over here, once I found that 4, I multiplied the 4 into the 13 and put it below. So that's the multiply step. And as I said down here, multiply the monomial by the divisor. So that this is a monomial. That's just a term that I haven't used before, so sorry, for a polynomial with a single term. So this is another polynomial term, which I probably should have said before. Monomial, binomial, trinomial. You'll probably hear people say those before. But polynomial is just a general term for a algebraic equation such as a polynomial with some number of terms. And poly, like polygon, is just means it's a shape with some number of sides. But if you have like a specific type of gon, like, or, you know, in the case of monomial means one term polynomial, bi means two, trinomial, quadrinomial, so on. That just kind of means a polynomial with a specific number of terms. So when I said multiply monomial, that's just what I mean for whatever I got from my match step, and that's going to be multiplied into the divisor, which is this. So 6x goes into x minus 4. And the thing that you have to remember is to multiply into both of them. Because if I'm taking a polynomial times something, it's kind of like over here, right? I had to multiply 4 by the entire number, not just the first number. So 6x times x is 6x squared. Assuming you're doing it right, those should always be a perfect match. Unlike over here, well, notice how the 5 was a perfect match. Technically, sometimes those numbers might not match, like 22 and 13, but it's not a perfect comparison. And then 6x times minus 4 is negative 24x. Again, it's not, that one's not a match, but that's totally fine. And so that would be the end of the second step. We're going to write that right below. And you always want to keep your terms aligned underneath the original polynomial by degree, because we're always going to be then subtracting. And with polynomials, you can only combine polynomial terms with the same degree. If they're not the same degree, they won't add. So alignment is important. It's kind of like over here. A lot of younger kids don't really know that with division, you're really supposed to keep the numbers lined up with each other based on place value. So when I did this over here, this is probably bad because I ran out of space. But anyways, it's not going to necessarily stop me from doing it. But basically, third step is to then subtract everything. When it comes to numbers, I didn't write subtract, and a lot of people will, but it's just sort of implied I'm subtracting. 54 minus 42, I'm looking for what's left over. And then I put like a line and subtract beneath it. But it's exactly the same with polynomials. You want to take the top polynomial and subtract the bottom polynomial. And so one way you could look at it is like this, as subtract the entire thing. But notice that one property we can't forget about with subtraction of polynomials is the distributive property, right? Because if I'm trying to just subtract this whole thing, as I did over here, right? I subtracted both numbers. I didn't add some of them. That would be ridiculous to subtract one column and add the next. But basically, you want to make sure to distribute the negative. When you're subtracting the multiplied quantity from above, both terms should change signs. And this is the shortcut that I recommend. When in the step of subtraction, change the signs. Change signs and add. So basically, I would not put parentheses on it like I did, but that's kind of that's the concept of what we need to do next, because we're always figuring out what's the difference between what I started with and what I'm putting above the line. But basically, I changed both the signs. I'll use green to indicate that I'm changing them. Oops, that one already was positive, so that one I need to change to negative, and this one I need to change to positive. And then it's a lot easier to add. So technically, you could just subtract them all, but I'd strongly recommend doing this. That way, now I can just combine like terms by adding. Adding is way easier. And this would make 6x minus 6x squared, which is 0, or we could say they eliminate or whatever. Or you could write a 0 below, but that's not necessary because it's gone. Just like over here, 5 minus 5 is 0. I don't write 0, 2, I just write 2. But then negative 26x plus 24x is negative 2x. And we've finished now with our first stage. And then after we're done with the match, multiply, subtract, now we repeat. We go back, match again. We keep going until we run out of room and reach the remainder. Same thing with a polynomial. And as we did before, I could put drop in there, but we always want to drop the next term so that we have another thing to work with as we continue. And now we're going to just switch what we're matching. Now we're going to be matching, again, you're only ever matching leading terms. So I'm going to be matching x with negative 2x, and then just repeat that process. So that, well, x would match with negative 2x by multiplying by negative 2, and you're always matching by multiplying, like what will that multiply to make that? Another way you could think of that, if that's kind of hard for you to figure out, is if you just take the first coefficient and divide by it. 6x squared divided by x is 6x. Negative 2x divided by x is negative 2. We're kind of breaking those divisions down into singular, easier problems to figure out. But anyways, match. Now I multiply, so I got to remember to take the entire negative 2, including the negative, and multiply into x minus 4. So that will then multiply to both of those terms, which would be, well, negative 2 times x is negative 2x. Those should always be a perfect match if you're doing it right. And then negative 2 into negative 4 should be plus 8. And the thing that's very easy to mess up with these is with the negatives. And so I urge you to be as careful as you possibly can with the distributive property and with changing the signs for step number 3. Because if you're making a mistake, that's probably where it's going to happen. There's so many negatives in changing the signs. So I still haven't done step 3. So first, I'm very careful to distribute my negatives. Then after I do that, I have to do step 3. I have to subtract all of this, meaning change the signs and add. So again, I'll do that in green, change the sign. That would become positive. That would become negative. And now I can just add them together. Those would eliminate, and this would give me 12 minus 8 is 4. And then once I'm basically at the very end, this is now my remainder, much like over here. Once I'm out of numbers, I'm done. But in this case, once the number I get has a lesser degree than what I'm dividing by, I can't multiply x into 4, and that's the point which I know I'm done with the division. And at the end of the day, we call this the remainder, and this polynomial we call the quotient, and this is called the divisor. And again, just in case your homework asks you for this is something I usually am not going to ask you about on an exam because I don't care. But you can also take the original polynomial and write it in this form in the same way. So if you took the divisor, which is just the fancy term for what you're dividing by, you multiply by the quotient, which is just the answer in the whole component, and then you add the remainder, exactly the same formula what I wrote right there, plus 4. What should happen is all of this should come back together and make the original polynomial. And this is one of the ways to check yourself. You want to know, how do I know if I did this right? If I multiply these things together, we would get, well, 6x squared minus 2x minus 24x would be minus 26x. Minus 4 times minus 2 is plus 8 plus 4. And notice that that would make plus 12. And so yes, it worked. It all adds back together. That's a quick way of checking your division out to make sure. And just in division in general, division always has that property to it where we want to see what comes through division and what is left over, if anything. And the last thing I'll say in this video is that like before, if we ever get a remainder that is not 0, we would say that these polynomials were not divisible. So back to the original problem, which I've now accidentally erased, we would say that x minus 4 does not go into 6x squared minus 26x plus 12, or these two polynomials were not originally divisible. And the remainder is always a way of checking. If the remainder is anything other than 0, those polynomials did not quite fit back together. And only in the case when it is 0, so let's just pretend it were 0, what we'd have is that would be gone. What it would imply is that those two polynomials multiply exactly back together. And the reason that's important is because it has to do with how the polynomial factors. And we're going to talk a lot about factoring when we talk about zeros, because factoring is a super important strategy when it comes to dealing with polynomials and understanding them on a very deep level.